Okay, I'm trying to. Simple is not here. Okay. Into. I'm trying to record this right now, but I need to restart the Windows. Okay, so I'm going to restart Team. So last week, how was your tutorial with the PyTorch and everything? How did it go? Did you now, are you now able to work on the PyTorch? Yes? I didn't really expect you to be able to do that because it was just a short tutorial, and definitely that actually we'll come back to the PyTorch and also many deep learning issues. Okay, so let me try to find my mouse. Okay, so let's come back to our course schedule. Okay, so last week was just a very quick overview of PyTorch and deep learning. Okay, and also the CGU AI platform. So I believe that have you tried to log into the CGU platform yet? Have you 你没有用过吗？有没有人想办法去登录？ You have an account already, right? Okay. In any case, you for this homework, you don't need to use the CGU platform yet, but for the next homework, you'll have to start to use that. Okay, so we'll come back to have some other lessons so that you can learn how to use the CGU platform. Okay. Today, what I want to do is to come back to our very basic concept of machine learning. Okay, and we will again go through the fundamental technologies. Okay, so machine learning, as you have probably experienced last time, was that if you have a lot of data, okay, and you can try to use different type of machine learning, okay, including the supervised and unsupervised, and also some other kind of the techniques, okay, and try to use the AI to help you learn the features, okay, to extract the features and then put it into the machine learning algorithm. Then the machine learning algorithm hopefully will be able to have the capability to, in the future, when you have some new data, the machine learning algorithm will be able to predict what the result should be. Okay, that's the whole idea of the machine learning. Machine learning is not just learn something they have seen, but machine learning actually is to be able to try to make predictions or try to generate output from something they have not seen before. That is much more important than just say, I've seen this, so therefore I know the result of this. They should be able to say, I've never seen this, but according to the data or according to the experience I had before, maybe the situation is going to be like this and that. Okay. And so therefore it's the prediction from some new data which is not in the original training set is something that much more important. Okay. And in order for us to implement this machine learning, okay, we have definitely different types of computer technologies that have been used for doing this job. And in the first lecture, we have some of the Python things, and I believe that most of you have already known from your study in the past that how to write Python programs. Okay, and Python is a very powerful and very dynamic and very flexible language. Okay, so it's very easy to use, and I'm not going to go through it, and I think you should be able to see this. These are the things. In Python, one thing about Python is that when you have a variable in Python, it doesn't have a fixed data type. Okay, the variable itself can have a data type. Originally, it was set to be an integer. And then when you try to say, okay, I'm going to make you to be a float, then you become to be a float. But at any time, you can also try to make it to be a string, or it could be a binary, and it could even be a list. Okay, Python is very flexible. Okay, and it has all these conditional statements, and you have the loops and things. But in Python, the fundamental data structure actually is a list. It's a sequence of mutable value. The values can be changed. The type can be changed. Even the structure. Okay, it could start with to be a scalar, just a single number, but at any time it can become to be a list. Okay, and the list doesn't have to be a fixed size. It could be very dynamic size. Okay, so the flexibility of Python is a blessing, but also is a curse. Okay, especially when we try to process a large amount of data. Okay. One thing about computer programming is that computer actually very fast. So therefore, in the past, that many things have been done using a loop. You can loop some operations for many, many times. For us, it's a lot of time for human beings. But for computer, actually, it takes a very short amount of time because it's so fast. Okay. However, when we try to do either graphics or when we try to do machine learning, even as fast as the computer we have, I've been talking about GPUs, still when we are trying to process gigabytes of data, when we are trying to process terabytes of data, it's still going to be too slow if we just use the regular way of, kind of handling that. Okay, that's why most of the machine learning or most of the AI these days, we are using GPUs, right? You know that everybody, when they talk about, say, oh, I'm going to build an AI system, then they will ask, how much GPU do you have? What kind of GPU do you have? Okay, and also, how much memory do you have in your GPUs? Okay, and so we want to be able to use GPUs because GPU can run in terms of processing a large amount of data. It can use the parallel processing capability. It can use the signal processing capability. So it doesn't need to be looking at each individual data one by one by one, okay? Which in the original Python, when you have a list, basically the idea is that you always look at one at a time, and you look at the next one, and you look at the next one. So that's why that when you create a list in in Python, you use append. Append is going to put in another one in there, put in another one. When you remove, it's going to remove from the beginning of the end. And it also has all this tuple and the set and dictionary, but originally is the whole idea of designing the Python language is to make it easy to write, easy to read, okay? But it's not really trying to a very fast programming language, okay? Because to human, whenever I, even I give it a big loop, if you take, 0.1 second to finish, to us, it's already so fast. But we can, you need to process a lot of data. That's not going to be the case. So another software that we often need to use, okay, when we are doing the AI or machine learning language, is called NumPy, okay? And again, I assume that most of you already have some experience with NumPy. NumPy is actually, originally, it was not designed for Python. It's actually just a numerical processing package. It's a fundamental package for scientific computing for Python. Okay, so in Python, I'm sorry, in NumPy, okay, the big thing about NumPy is the numerical processing. So NumPy actually has a lot of mathematical functions defined. We can also have random number generator. It can has, a built-in primitive for a lot of linear algebra routines, matrix multiplication, matrix dot, in the conversion and inversion and this and that. It also has Fourier transform, signal processing. A lot of the mathematical library are already built in inside of this numerical package. Okay, so originally this NumPy has nothing to do with Python. It's actually designed more for C programming language. Many of you probably have from C or C++. Okay, and even maybe well you know that we have many different programming languages. Java. What are the what is the kind of the application domain that use Java the most? Is it scientific computation? Do we use Java for scientific computation? What is the most kind of big area that people are using Java for? I'm sure that all of you have learned Java, right? Or you have heard of Java, right? So who will be using Java? Machine learning? Has anybody written any machine learning language application using Java? Why not? Because it's not designed for machine learning, but what it's designed for. Java was and I think still is a very popular programming language, right? So what is Java good for? Who uses Java? Who is the biggest customer in Java for using Java? Give me a company. Netflix, okay. And but Netflix actually is not really an IT company. Whom do you think will be, Java will be their major programming language? IBM, right? Companies like IBM, like Oracle, okay, have you heard of Oracle? Processing data processing, database. Java is good for database processing, okay? Oracle and companies like SRP or what, S something, I can't remember them. Okay, or probably the company that doing a lot of office applications, they will be using Java. Okay, and probably some of the government systems were built using Java. Okay, but Java is not good for number crunching. For number crunching, what would be the popular programming languages to use before Python? For engineering students, not in computer science, engineering student, what language do they study? They need to study. C or C++, right? C++, those will be for number crunching. Those will be engineering programming languages, okay? And so NumPy, before it becomes to be something to do with Python, actually, it was built for C++, okay? The same thing as we will see that later when we talk about this Torch, okay? Torch actually was not built for Python. Torch actually was built for C++ first, okay? And later, because Python has become to be so popular, they port Torch and also this numeric thing into Python, okay? So actually, the thing about the NumPy, okay, is offer this mathematical functions. It has a lot of this routines for Fourier transform and for signal processing and a lot of mathematical things, okay? It's the good thing about that is that it's able to do vectorization, okay? It is able to do things very fast, okay? and is able to kind of take, when you have a lot of numbers, okay, numbers not like Python, which is individual, but the numbers are big matrix, like a big, array of something, then NumPy, okay, will be able to handle. It supports a wide range of hardware and computing platform and this and that, okay. However, okay, NumPy, what is the most important type of GPU that we use these days? From which company? NVIDIA. Okay, but NumPy doesn't have automatic, okay, because NVIDIA, what is the native kind of programming that platform that they use? What is the language? Called CUDA, right? CUDA is actually is a almost like a machine code for NVIDIA, right? So in order for you to run something really fast on that particular kind of hardware, you need to use their machine code. Okay, so for most of our AI right now, okay, if you want to use GPU, then they will ask, what kind of GPU do you have? Okay, and if you want to use NVIDIA, that means your program need to be translated into CUDA so that it will be able to run natively on NVIDIA, okay? For NumPy, it runs on many different kind of GPU, okay, but if you go to the NumPy hardware, the company's the website. Okay, hold on. Where is my mouse? Okay, if you go to the NumPy, okay, and then you would check to see that it would tell you right now it doesn't really have let me see, install. Okay, if you look at this install here, okay, documents, build the source, verify the install. Okay, somewhere. Okay, you can install using pip and conda. Okay, and but somewhere I don't remember where. Okay, but you can see that it has the Mac OS, it has Windows, but it doesn't really have NVIDIA. You also can use all the non-Python library, the tool you may need, okay, and such and such. Okay, so what I'm trying to say is that NumPy actually was built originally internally, actually using C++, okay, but actually Python is not the original language. Okay, so what's the difference between programming languages like Python and the C++? Okay, here is an example of I have some history about NumPy. Okay, NumPy was originally was built in the 1990s and much earlier than that. Okay, but later it tries to re-implement this. Okay, eventually for for the Python community. Okay, so if you look at NumPy, the basic data structure is actually called array, right? Do we have array in Python? No, I already told you. Python has list. When you create a list, do you need to tell list how big, how many elements it has? You don't, okay? But when you use array, for some of you, if you have ever written program in C++, when you create an array, do you need to know how many do you have? You need to have create some size of an array, okay? So therefore, okay, whenever you are using a NumPy, okay, or you're going to be using PyTorch, okay, the size of the array here, you can see can't change, change. Okay, the size of array, when you create an array in C or C++, you cannot dynamically say, oh, I'm going to have 10 now. Oh, okay, I'm going to change it to 100. You need to create another array, which is a fixed size. Okay, so all elements in the array must be of the same type. That's again, inside the list of a Python. You can have integer, you can have floating point number, you can have string, you can have this and that. But in an array, okay, all array, the data in the array must be of the same type. Okay, you cannot really create an array to say, oh, inside of this array here I'm going to have some numbers, and here I'm going to have some characters. They cannot mix. Everything needs to be of the same type. Okay, that is very important. Next time when you write your program in PyTorch or in using NumPy, before you put the information into the array, make sure they have the same type, because those are going to be the information are going to be put into some processor, whether it's GPU or whether it's just some CPU, something. It's going to be running using the same operations. That's the power of this big array. They are of the same type, and they need to know exactly how big it is, so the system can decide how many am I going to take to run at the same time. Okay, so if I have a 1,000, array of 1,000, and if I know that inside my GPU or inside my CPU, I can process 100 at a time, then you would predefine them into 10 pieces, and then we'll do this 10 times. But if it doesn't know that how big is your list, then it cannot try to use the strategy to parallelize it. And then your speed cannot be so fast. You have to kind of always test to see how big it is. And then you say, okay, now I'm going to use how many GPU and this and that. Okay, so the shape, okay, inside the NumPy array, okay, it can have multiple dimensions. That's why it has the ND array. Okay, ND array means the dimensional array. So you can have different dimensions. You can have one dimension, which is scalar. You can have two dimensions. You can with matrix, and you can have 3 and 4. But the number of dimensions and also the size of the array needs to be pre-known. You need to create that. Okay, and once you create that, you don't change it. Okay, once you create the total size of the array cannot change. Okay, and the shape must be rectangular, meaning that you can have 2 by 4 by 5, but you cannot have this 2 by 4 by 5 somewhere in there. There will be 2 by 3, okay, by something. They need to be exactly, everything needs to have some value in there. You need to be totally filled. Each row of sorry. Okay, each row, of the two-dimensional array must have exactly the same number of columns. You cannot have something which is 1 is going to be 1 and the other is 3 and the next one is 5. You cannot do that. Okay, so when you say this is called created array, okay, the array here, if it started with the size of 6, then it will be 6. Okay, it will not be. You cannot have say, oh, I have 1, 2, 3 here, and the next one here, I'm gonna another one which is gonna be just 3 elements, and the next one is gonna be everything needs to be exactly the same uniform. Okay, and so when you create an array here, you can see that okay, we have array and which is going to be, and inside in each of them is going to be the same. Okay, and you can have, it has the primitive to put all of them to be 0 or 1s, or you can create them to be all empty. Empty just means it doesn't have a value, but still the size, okay, is fixed. You need to create an array, and the array say, okay, now the array is going to be this particular size, okay? And the good thing about NumPy is that you can use primitives, which such like this, okay? So your A here is an array, But inside array, you can use this a less than 5. So if you use the Python syntax, this is wrong, right? A is supposed to be an array. So how can I do a less than 5? Does it make sense? It doesn't make sense in Python. Okay, in Python, if this is going to be a multiple number, I cannot compare multiple number with a single number. But in NumPy, it allows you to do that, to say, oh, this actually is going to try to get all things from this array with the value. This A here means in each specific one is less than 5. Okay, and this is the same thing. Okay, 5 up is equal to A greater equal to 5. And what does it mean? It means that I'm going to get part of the array, but inside the array, each of the value needs to be greater equal to 5. Okay, so you cannot look at this in Python idea. Okay, because this is already a special type called array. Okay, so array is no longer, this A here is no longer a regular variable like in Python. Okay, but this now has some special property in NumPy allow you to be kind of playing with the array and yet access every individual elements inside of the array. Okay, here, okay, is creating another, this is going to be from the original array A, and here A percent 2 means that modulo 2 is going to be equal to 0. So this is going to get everything, which is what? Which is an even number, which is going to be even number. So therefore, this one here is going to take a subset of the array, okay? And the subset array, inside that subset array is everything is going to be an even number, okay? So when you use NumPy, okay, don't look at that to be like Python program only, because if this is Python program, Python would give you, say, wrong. You cannot do that, right? But if you import NumPy, then you will be able to use a lot of this kind of primitive to say, I'm going to be looking at an array, okay? And so inside an array, I can use this very, high level concept, which is going to be, I don't need to go to each individual components, but I just look at the whole array to say, okay, whatever inside of the array, when you satisfy certain property, come back to me or come to me. Okay, then I'll be able to simply get the information directly using just one line. That's the power of this NumPy, okay? You also have the idea of the broadcasting. Broadcasting is a special kind of a primitive that allow you to be able to say, oh, I have two different array, which is a different size, okay? In Python originally or in other languages, you need to have them to be exactly the same size so that they can be, kind of be multiplied, or they need to be added or something. But broadcast says that, well, if you have one side which is a little bit bigger and the other side a little bit smaller, don't worry about it. The smaller one will be kind of expanded virtually, just like it's a bigger one, the same bigger size, okay? And then I'll let you, go together. Some of you, I don't know, your lives are so different from mine. Like, have you ever gone to some dance party? When you go to some dance party, okay, and you might have the number of boys and number of girls, right? Okay, when you have a dance, one boy will match with one girl, right? Okay, now it doesn't happen all the time that number of girls and number of boys are exactly the same, right? Never really the case, okay? So sometimes you have more boys or sometimes you have more girls. Then can you still dance? Well, you just match up whoever is, kind of can match up. So you have more boys and more than girls. all girls can be matched with the boys. Okay, the rest of the boys, what do? You dance by yourself. You don't have a partner, okay, but still we can have everybody to be dancing. Okay, that's the idea of the broadcast. Imagine that you have some boys which doesn't have a girl partner. Okay, you can still behave just like you have a partner dancing with you. So you don't try to force them to say, well, we need to have exactly the same number of boys, girls and boys together so that we can have a dance party. We're going to have a dance party anyway. You know, boys and you have 7 girls, so be it. Okay, the rest of the 3 boys, you don't have girls, but you still can dance in the same way, just like those boys with girls. That's the broadcasting. Okay, so broadcasting is a mechanism allow NumPy to perform our own array of different shapes. Okay, some of them they may be 2 by 3, and the other one is 2 by 4. So 2 by 3 will be extended just like it's 2 by 4. And then 2 by 4 and 2 by 4 can kind of be performed together. Okay, so when the number of dimensions, okay, is they must be compatible. So you can have 3 by 5, and this one here is 7 by 9, then it's going to be a problem. But if one is 3 by 5 and the other is 3 by 6, then they are still compatible. So we'll make both of them to be like 3 by 6. We can extend a little bit more. Okay, so there are some of this interesting idea broadcasting. If you go to look at some of these things that you'll be able to find out. Okay, so I'm just want to give you some ideas, and and also NumPy allow you to be able to kind of try to change the shape, even though I told you at the beginning, okay, array need to be of a fixed shape and fixed size, but it does have some special primitive to say originally 6, but I can change it to be 2 by 3, or I can change it to be 3 by 2, but the total numbers should be the same. Okay, so I can move one big chunk of number into different type of shape, okay, by specifying, say, okay, I'm not going to be changing value, but I'm going to change you in the specific locations. So at any time I have this one here, which is a big single dimension numbers, okay, I can put you into a different, method by say using reshape. Reshape would allow you to put them into something which is like this or like this, so that you will be able to use the matrix multiplication or dots, okay, and using those operations designed for 2-dimensional matrix, okay. And there are many different tutorials. You can go take a look. So for example, like I'm sure that if you go to the NumPy, there will be documentations, there will be things, and you should be able to find a lot of examples to look at. Okay. PyTorch. Okay, so last week you have been given this very quick tutorial of PyTorch. Okay. PyTorch, the NumPy is designed to be providing numerical capabilities to handle the metrics, to do all this big number crunching. And PyTorch actually is designed specific for deep learning. Okay, again, it was not really designed for Python at first. It was just Torch. Okay, it was designed for other programming languages, and later it was ported to Torch, to Python, because Torch is ported to Python because everybody is using Python to write their machine programming code. Okay, and since it is designed specific for deep learning, okay, so therefore it has many pre-built deep learning model included in the Torch, okay, or in the PyTorch. So you can go to PyTorch Hub, okay, you will be able to find, say, for example, Torch Vision. So there will be a lot of computer vision models already built in inside of the PyTorch. So if you want to do a very simple, something, you don't need to write your own. You can just go to PyTorch and you'll be able to find something from the library, okay, and you'll be able to do this and that, okay. Originally, it was produced by Facebook, or now it's called Meta, okay, and actually, originally, it was not really designed by Meta, but later on, Meta decided to adopt this and then make it open, which is a strategy for Meta in many of the AI software. They are willing to make it open, and PyTorch now also is used not just by Meta but also by many other companies because it's supposed to be a open platform. Okay, and so this is a little bit of history. It was actually first by two different framework, Caffe 2 and kind of other things. Okay, and so therefore later it was kind of merged together by Meta and then Microsoft. Okay, and they become to be Caffe 2 and merged into the PyTorch at the end of 2018. Okay, and now of course that everybody is using PyTorch because it's actually an open platform that everybody can contribute and everybody can adopt without paying anybody for that. Okay. So I know that you have been given. Let's see if it's here. No, not here. Is it? Okay, so this was something that you have gone through last time, right? Okay, this is the notebook file that I believe they have gone through these things, and so you can see that when we use PyTorch, that you need to import NumPy first, and you need to import Torch. Okay, and this will get both the numerical, which is a lot of the metrics calculation, as well as the Torch, which actually has a lot of the deep learning kind of primitives. Okay, and so I believe that this was the link has been given to you on our Teams, so you can go to study many of this yourself. Okay, including many of this matrix computation and things. Okay, so please try to practice this yourself. Everything about PyTorch in terms of the tensor, in terms of all these different things. Okay, and later on we'll come in together to look at the linear regression part to use the PyTorch. Okay. Okay, so in today's slide, I have also given you some extra links to different videos. One of the videos is about linear algebra, okay, because that when we are writing the machine learning algorithms, we need to use a lot of this linear algebra primitives, okay, and you can go to this PyTorch fundamentals for the different framework, okay, and you can see that there are just so much material, so different on the website that on the internet that you should be able to learn by yourself. Okay. Okay. Before we stop for the break, homework. Homework 1. Any question? Any problem? Or are you done? I thought that in the code. Yeah, but the code actually has a plot, right? So what do you mean you can? You want more example, meaning the maze? Okay, let me put it this way. In the homework 1, we ask you to be looking for paths to different cities, right? So the program already built in the output is going to be printed with the dots, right? Already you can see that whether your output can reach all cities or not, right? Because in this homework, I didn't ask you to find the shortest path. It's not in the requirement. I just need you to find a path using either the breadth first search or depth first search. Okay, let me repeat this. 在这个作业，我们要找的那个路是 reach A、B、C 3个不同地方，对不对？你只要有一条路能够 reach 到这3个地方就可以了。我并没有说要最短路径，我并没有说你一定要用 breadth first 还是用 depth first search，你就是找到。So all you need to do is after you have finished, then you look at your output. If it has a way to find every city, okay, the only thing I require you to do is to show them in different colors, right? Yeah, right. That is true, okay? That is true. But from the starting point, you reach the first city, then you will never come back to the first city, right? I mean, never come back to the starting point, right? Mm-hmm. Mm-hmm. Okay. Some overlap. Some overlap. You wouldn't be a complete overlap, right? No. Okay. If you trust your result, okay, because like I said, that your program, when you submit your program, we will be using our own data set to test your program. So we definitely will be using something which I can see that the paths are correct or not. 你懂吗？就是说，你们现在用你们自己的 test data set，它可能那个路径会一样，可是你拿过交上来以后，我会跑我自己的 test data。我在我的 test data，我可以看得到你跑的路线是不是对的。So the example test data, what I call it, HW1 map.txt is just an example. You should create your own different examples for testing your program, because when you submit your program, we will be using our secret map to test to see whether you can find the correct result or not. How big is our secret map? I don't know. It could be 100 by 100. Okay, and we may, put the cities in such a way that definitely should be different path. We could have different city A, B, and C in different part of the map. So you just need to make sure that your program actually would always find a path which can go to all cities. Yes, anything else? So I think I understand your question. You say you cannot see.
And there is one node between them. If we go ahead, it will be reached to some other city. If we go left, it will reach.
Yeah.
So when we are going to B, it will take yellow color. But when we are placing back and go from B, we are going to C. So if we go back to the same path and from
Right.
the half path will be overlapped.
Yeah. The overlap will show in the color, okay, which is going to be your last path, right? Okay. So if I have a map, right? So I have one route going this way to reach that. And then if I go to next city, it might be true that I will come back, but you will not come back to the S. You will come somewhere and then go to somewhere else, right? So I should be able to see that. So let's say that the path, the last path would always show a complete path. But the previous path, maybe, the color will be covered by the. So if you say, for example, if I ask you, say, I want to go to A first, then go to B, then go to C, then the path from B to C should be complete. But A to B may be covered partly, but I can. State A and state B will be the same color. Yeah. Okay. 我用中文再说一次。Okay, sorry, that's for me to repeat this in Chinese. 三条路径呢，一定会有一些地方可能会互相会交叉。OK，所以你在最后的那个颜色呢，的确有些地方是会被盖过去，对不对？后面的路会把前面的路盖过去，那没有关系啊，因为我还是可以看得出来说你原来路是那样走的。OK，当然是盖过去的地方就是只会秀最后一条，所以最后的那一条路一定是一个完整的路，可是前面的路有可能会被前面盖掉。OK，所以我们是 human。我们 human 可以看到你走出来的路是不是一个可能的路线那样子。Okay, so just write your program so that you have that kind of a capability to show the path in different color, and in our test file, okay, in our test file, we will be using data which it will show 3 different paths. If you are using, kind of a reasonable algorithm to doing breadth search or depth search, definitely that you will be showing the complete path. Okay. Okay. Let's take a break and then we'll come back to continue. Okay, so let's get back to our lecture. So the second part of today's lecture, actually, I'm going to be using the material, which, as I have already told you, that we're going to use material from the Harvard University CS50. Okay, and so some of the slides will be actually using this one, which is from the week 4 of the CS50. Okay, So later on, that if you want, you can go to watch this movie, which actually not movie video, which actually has a probably a much more detailed explanation than I will do today to talk about learning. Okay, so learning. This is big. I'm sure that again that you already have a little bit of the experience, but we'll look at more detail later. So learning in general, we can classify them into different type of learning, including supervised learning, reinforcement learning, and unsupervised learning. Okay, and so let's start with the supervised learning. So supervised learning, by the name supervised, means that you already have some information. Okay, given you have some input, your system already know, or you already know what the output is supposed to be. Okay, so when you are provided with input data, okay, your data actually will be input and output pair, that everything is already known to have, whatever is the output. Okay. So for supervised learning, one of the type of job that we often try to do is called the classification. So given a set of input data, then we to see that particular input data, whether it belongs to a certain type of information. For example, when we look at pictures, we say, oh, this picture here, it should be a cat. And look at this picture here, it should be a dog. Okay. And this, if you look at some other things, you'll say, oh, this is actually a horse, or this is a car. Okay. So classification, the output of the from the input information, whether it's an image, whether it's some feature, or whether it's something, should be one particular class. Okay. So one example is that we want to be able to predict, okay, whether it's going to be raining or not raining, in a certain day. And so we might be given some input information, which is like this. We might have some recording from the certain location that at a particular date, okay, what is the reading of the humidity and what is the reading of the pressure, okay? And then there will be a recording whether there is rain or not on that particular day, okay? So we might be given, for example, some information like this. On January 1st, our recording humidity is 93, where pressure is like this, okay? And we also have recording that day is a rainy day, okay? On the other day, you have less humidity, you have this, and then recording says no rain and this and that, okay? So once you have information like this, then what we're going to do is to try to train a machine learning algorithm, okay? We're going to try to look at the humidity and the pressure on some specific day. Then we predict to see that whether that day should have rain or not. That's the classification. Okay, so you have some input information which will be recording the humidity and the pressure. Okay, some other problem that you might have some extra information. Depending on how much information you have, all of this will be considered to be your input data. Okay, then from the input data, we want to be able to predict. Okay, suppose I give you some day with humidity and pressure, your system should tell me whether it should rain or not. That will be the weather prediction. Okay, so mathematically it could be like this, that we have already know some information about certain humidity, certain pressure. Okay, and we know the result of that to be rain. So we have the value of this particular function, which is quote unquote the perfect function. Okay, given that because we know this is true, this is for that day there's a humidity, there's a pressure, and we know exactly the result should be. Okay, so we should somewhere in the universe maybe there is such perfect function which can predict always correctly. Okay, whether you have rain or not. However, okay, we are going to try to ask the computer to say, could you build us such a function? given your input information, can you make a prediction, okay, on the rain or not on that particular day? And this function, they will be computed by our program, okay, or by our system. We call this to be edge. So the effort, the engineer effort, to try to find an edge, we will get as much same result, as many similar result as the app, given exactly the same input. That's the idea of the machine learning. Okay, so so you might have from your input data that you find that there are a lot of this humidity this way and pressure this way, and when we have the rule, and then we have some extra information here. Okay, there will be certain days that the pressure is this way, humidity this way. Okay, and it turned out this is to be rain. But you can see that from this. Okay, when we look at this by human eye, okay, we said that there seems to be some kind of distribution, okay, or some kind of tendency that we can find, okay. But as we also know that, okay, no matter what kind of mechanism you have, okay, when you try to see that certain days like this, okay, the humidity and pressure seems like it should be a rainy day, but the recording says it's not raining. Okay, and so the question now is that, could you, find a machine learning algorithm, okay, which will be able to try to, if I give you another humidity and another pressure reading, can you predict to see that whether that day will rain or not? That's the machine learning. Okay, machine learning is trying to say, from all the information we collected in the past, and now we give you a new day with some new information for the input. How can you find out? Can you predict what this is? Okay. So to do this, there are many different ways you can do it. Okay. So one way to do it is to say, well, yeah, look at this one here. If I don't ask you as a machine, but ask you as a human, suppose I'm reading like this one here, what do you think? Is it going to be a rainy day or is it going to be not rainy day? So most of us, I guess, will think that this will be a rainy day. Why? Because from our human mind, we have this tendency to say, well, if everything around it, okay, turned out to be a rainy day, and this is the day that has a condition just right to have rain, okay, it most likely you will be raining, okay? And so this is what we call as nearest neighbor classification. Okay, nearest neighbor classification is to say that whenever you have new data point, whenever you have input feature, okay, you most likely will be looking at whatever is the situation very close to that particular instance, okay, and say, well, because it is close to that, you have the similar condition, so therefore the result should be the same. Okay, and that's the idea of the nearest neighbor classification. So given an input, choose the class that is the nearest neighbor, okay, nearest data point to that particular input. Okay, so in our particular case here, okay, so suppose I give you this one. Okay, so then you look at all of the data points we already have, okay, and we try to find that among them, which it would be the dot closest to this one. And by our visual, it could be this one, it could be this one, right? And these two should be the closest to this one. Okay, so in any case, if we say this one is closer to this one, and this one here says it's not a raining day, then we should make the prediction to say probably it wouldn't rain. Okay, that's the idea of the nearest neighbor. Okay, and like this one here. So this is actually is a sticky point, right? This is a little bit ambiguous. Okay, so we actually have a point here, okay, and this data point here with this particular humidity, with this particular pressure, and it is sitting. If you find the nearest neighbor, they will say it's this, and that particular day is not a raining day. And so according to the nearest neighbor, it should be the same as the nearest neighbor. So therefore, the prediction should be not raining. By human decision, do you think it should be raining or should not be raining? I think most people probably would agree with me. Okay, even this day is raining. I mean, not raining, but all these days are raining. So it probably will rain more likely than not rain. Okay, it probably will be, even though this has been reported to be not raining, but maybe there are some other conditions, or maybe the recording is wrong. Okay, so nearest neighbor, okay, sometimes would kind of give you the prediction according to the algorithm. And we know that the algorithm is not always correct. Okay, so sometimes that, we may want to say, well, yeah, I think it's going to rain, okay, because, okay, we don't look at just one point. We should be looking at more points, okay, so we can extend the original nearest neighbor to say, well, let's not look at just one, okay, because it could be happening that you're next to one which actually is an exception. So maybe let's try to find more, okay, nearest neighbor, and then see how they go, okay. So so you could be, for example, like given some input, then you choose, the out of the care nearest neighbor. So this point, okay, then I look at those neighbors, okay, I'll compare them and look at what is their current reading. Okay, and then out of this care nearest neighbor, we take the most number of them, the majority of them, and make that to be our decision to say, oh, okay, I think that's going to be the case. So if we come back to the cases like this one here, okay, so even though we are trying to look at this one here, if we say included like 3, then we'll probably find this one, and this one, right? And so 2 out of 3 says it should rain, and so therefore we'll make a conclusion this one here should rain. Okay, and if we include 5, then it could be this one. I don't know, between this one and this one. Okay, maybe this one a little bit closer. And so out of this, okay, 3 of them will say rain, and this 2 says not rain. Okay. So in any case, neither of this is always reliable. Okay, and that is just a situation for most of the machine learning. Okay, because the input data that we have received, okay, even though they are the ground truth, but the ground truth sometimes doesn't have all the information to be making the right decision. Okay, because we know that, to decide whether you rain or not, you may not be counting just the humidity and the pressure. Maybe something else, maybe how windy it is or not, or maybe, there will be some extra, kind of a situation that make that particular day to be something, special. Okay, so machine learning, however, can only use some algorithm and try to make a decision. And that's also why that a lot of time that when we say machine learning, then we try to find as many input information as, or data points as possible, because the more we have, hopefully it will give us more correct situation. Okay, but again, it doesn't guarantee, because if you have, your information, you have more information which is going to be all on this side or all on this side. then it still doesn't help when you are in the middle here. Okay, so just because you have more information, it doesn't mean that you are going to be able to make a better decision. Okay. So k-nearest neighbor. Okay, the other way that we can try to make a decision is to say, well, not just rely on neighbors, but look at kind of a broader picture, okay, and see that we can find some way to be dividing them into, that's what we call classification, classes. Okay, if we have some way that we can find some way to say, okay, they are divided in this way, okay, or something, then then when you have a new node, which then we can decide whether it will fall into this side of the line or that side of the line. And if it falls into this side of the line, then we'll say, oh yeah, this one here should be the output should be something, okay. But again, this is from the original input, okay. So when you have original input data, how do you find this out? Okay, you can see that in this particular input, data set, it's almost impossible for you to find this very clean-cut line that all data points will easily fall into one or another. Okay, and so it also may have the so this is like we are trying to find here on the X2, we're trying to find the edge, and this edge here should predict, or it should give us the output to say this one here should be greater than 0 or less than 0. Okay, if it's greater or equal to 0, then we'll report it's random. And if this is reported to be less than 0, then we say this is not random. Okay, and so this one here, one way to define this edge here is given this x1 and x2, then we come up with 3 parameters, w0, w1, and w2. Okay, and this is what we call as a linear, okay, linear function. The linear function here is to say that if we can plug in, if we know the value of w0, w1, w2, then we plug in x1 and x2 into this linear equation, and we see what the output is. And if the output is greater than 0, then our prediction will be that this is going to rain. Okay, otherwise we say it will not rain. Okay, so how do we find this W0, W1, and W2? Well, it's just mathematics, right? Right. Well, you can try to use mathematics to find this, okay? Or you can try to use, some kind of machine learning algorithm, okay? And to say that, well, I don't know what is W0, W1, and W2, but I'm going to try to use some algorithm, okay? And this algorithm here would just say, I'll give you some random W0, W1, and W2, and let your algorithm try to change the value of the W0, W1, and W2 so that it becomes to be more correct, okay? And that is going to be something that, is going to be like we are creating a system, which is going to be, we are trying to find this W, which is going to be a matrix, okay? And we're going to have this W here multiply into X, okay? And this one, X here is going to be your original, this is going to be 1 and X1 and X2. So you have your input vector will be 1, X1 and X2, and your weight vector will be W0, W1, and W2, okay? And so now this is something now you are kind of can start to see that this is exactly what, when we talk about models, that a lot of time that, we have weight, okay? And then we have input vector, okay? And then we have this multiplication, okay? Because when you multiply this one here, it will come in to be exactly like this one. And this one here is going to give us some result, and we're going to have the result, which is going to be making our prediction whether it's going to be true or false, whether it's going to be class 1 or class 2, and such and such. Okay. So in the machine learning, okay, we are going to be using something like we have this W here, okay, but we're going to try to come up with a way, okay, that will be able to update each of this W. Okay, for us to be updating each of this W here, we know already that we have the Y, which is the correct result, because we have the original output. Okay, I mean, this is supervising, so we know what is supposed to be the right output. Okay, and we have some initial W, okay, which will give us this H of X W, okay, HW of X, okay, because given us an X, okay, we know what our current prediction will be. Okay, so from this and this, we can see that whether they are the same or not. If they are different, then we know that somehow we should change the W, okay, so that the W can become to be something. If this one here is already 0, then you can see that this 0 here, already is perfect. Then by doing this multiplication, even the time into the XR here, you wouldn't change the weight. Okay, so that particular weight is already perfect, then we don't change it. But if this way here, the result is because your current prediction and your current output, I mean the ground truth, they are not the same. They will try to see that, okay, how can I change the W in such a way that the final output will be closer to 1. Okay, and that's how we are trying to take the actual value, okay, minus what is the current estimate, okay, and then we can use some alpha here to say this is going to be a way for us to be deciding that how much change, how comfortable or how heavy we want the difference to be influencing into the weight. Okay, and if we continue to run this over and over again, we will be changing this W from some initial value, and that initial value, it could be randomly generated at the beginning. Okay, but by doing this one here, we will try to make this actual value and estimate to be getting smaller and smaller, and eventually, if this one here is 0, then the WI wouldn't change. Okay, and that will be our final output. Okay, so but in terms of the output, okay, usually we have the W times X, which is like this one here. Okay, W times X is going to be our if we have a weight matrix, okay, when we're given an X, okay, a set of input value, okay, this one here would tell us the decision whether it's going to be a RAN or no RAN, okay. But we know that in many of the situations, because we are not really going to have a perfect model, okay. So probably when you try to produce the output, okay, you're going to fall into something, like this one here. You're going to have some values which is, it's absolute. Here is probably going to be, okay. So from you using our model, we probably want to have something which says, I think there's a very high probability it will rain, or there's a kind of not so big probability it will not rain. Okay, so like if we have this, okay, then we'll produce the output. Okay, like this one here. Okay, the chances for this one here to be a raining day, okay, because it's closer to here, is probably lower than for this one here. This one here, the chances for this day to be a raining day is probably much higher. Okay, so from that, we probably want to change our output from the W times X instead of strictly just 0 and 1 into something a little bit like this one here, and this is the code like a sigmoid function. Okay, so we would, given this W, current W, and the input, okay, that you will produce an output which is not an absolute 0 or 1, okay, but you will be something, say, okay, you are very sure that it's going to be 0, you are very sure there's a 1, but probably somewhere in between is getting more and more likely it's going to rain, you know, or less and less likely it's going to not going to rain. Okay, and in our system, okay, because after all we're doing the machine learning, okay, and we all know that probably no model is 100% perfect. Okay, so most of the time, okay, this is probably not going to be as good as if we produce something like this, which is you have a soft threshold. Okay, so even when you are trying to do the machine learning to the computation, okay, you value, then your output value, you probably will be making the prediction, okay, but your prediction, rather than using a hard threshold, you will be using a soft threshold. Okay, so so what we have just said is that if we're using this W0, W1, W2, it's basically just like we are trying to come up with this particular line. It's a linear decision, okay, based on the value of humidity and the pressure, okay, and we use the W, okay, and we add this together, okay, so we have this linear line here to be separating the two, okay, and of course, that this one here would give us the decision which side of the dust will fall into, even though that we can try to soften the decision to say that this one here is most likely, okay, going to rain, but it's not always sure. Compared with this one here, you know, this is very sure that it probably will be raining, and this one here is most likely, or the likely is going to be raining, okay? Another way to try to kind of try to do the machine learning is to use something called the support vector machine. So support vector machine, I will not talk about the mathematical detail today, but basically it's going to be something like this. Now, suppose that you have two different, you have a set of information like this. You have this and you have this, okay? We can use the same way to say, okay, if we use the linear way of separating them, we will be trying to draw the line, okay? And you can see that we can draw the line this way, we can draw the line this way, and this way. We can have many different ways to draw the line, okay? All of them, when you are given this data set, okay, will give you perfect result, okay? Because you can draw the line this way, you can draw the line this way, you can this way. They are all going to be okay. Okay, but again, from our human, kind of things, okay, you can see that probably this line is better than the line we have just seen. Because this one here, you can see there's a tendency this way, there's a tendency this way. And yet, even with a line like this, okay, we can have the line in many different places. And this one here probably is a better line than here, right? Why? I mean, if you have to choose between this one and this one, which one would you choose? This one, right? Why? Reason. Because we know that, okay, we have input data, which even though the previous line can make correct predictions, but in the future, we'll have some new input data. They probably will be somewhere in here. They probably will be somewhere in here, okay, and this and that, okay? So if you have a line like this, then you might be making a lot of decisions for points like here to say that they are going to be raining days. Okay, but you can see that probably one here in the future, new data, this would give you a better answer than the previous one. Okay, and this is the idea behind SVM, support vector machine. I'm trying to find a, kind of a separation between the two, and so that the distance between all of this to the line is the largest, meaning that this line here is in the middle of acceptable boundary. Okay, trying to make it to be as in the middle as possible. Okay, if you move this one closer this way, then you will be too close to this cluster. If you move this one here, it will be too much to that particular cluster. So what it means is that when you are doing the machine learning, a lot of time you are not going to be satisfied with just your current input data set, because you should be expecting your system will be used to make predictions for some new data. And that new data, you want to give your system as much flexibility or power as much as possible, okay? So that you will be able to make better decisions for unseen data, okay? So support vector machine has mathematics, okay? And sometimes that, it's trying to find what we call as the mixed margin separator. That is the boundary that maximizes any of the data points. Okay, that particular line is not so close to this, not so close to this, but it's kind of give itself a larger boundary. Okay, so let's look at this one here again. Okay, support vector machine is a mathematics. You'll find the line in this way. If you can also try to say, okay, this line here can be tilted a little bit. Okay, but if this line here is not this way, but it tilted in this way, what do you think is going to be the total distance between dot points and the line? Because some of these points here will probably be too close to this line, if it's this one, and some of the points here will be too close to this way, right? But if you tilt it, the slope is in this way, then the total distance, okay, from all of them, or not so much of total distance, but the boundary, okay, between the two, okay, will be the widest. Okay, the support vector machine is a very powerful, very useful algorithm to use. We want to go into the detail today, but I just want to show you that that's another way to be coming up with a model, okay, to be making the predictions. When you have like, okay, if you're using the linear, classifier, you wouldn't be able to find an answer because it's not linear. There's no linear way for you to be finding a way to do this, okay? But if you use the support vector machine, you may be able to find the boundary which is like this, okay? Support vector machine doesn't need to be linear, okay? It's not going to be using this particular model, okay? So what we have just said, those are the machine learning that given them input, okay, then you can make decision whether it's going to rain or it's not going to rain, okay? But in many of the machine learning things is that we want to be able to learn a function which will be able to map an input into some value rather than just yes and no, rain or no rain, okay? And this is what we generally call them to be regression. Okay, so for example, here we have some information about how much use the advertising in the business, and then you can see that we will try to see that what kind of revenue or what kind of benefit you get. Okay, usually, of course, the more you spend, the higher that you're going to get your return, okay? And here, this is in general the case, okay? So now the question is, suppose I want to be able to just say, well, this year I'm going to make a budget. Okay, so rather than just say yes or no, it's going to be how much I should spend on the advertising. Okay, or let's put it this way. If I give you a number to say that I'm going to spend, say, for example, 2,000 rather than all the three numbers, what do you expect to be your revenue or your benefit? Okay, and this, so therefore you can see this is going to be the kind of machine learning that we're not trying to make a decision yes or no, but we're going to give you some input information, and we expect the machine to come up with an answer, which is one of the value in a continuous range of the values, okay? And so this is called the regression, and the regression is something, maybe something like this. Suppose that we have some already known that some advertising budget, and this is the sales that we have received. So we still have many, many, many different points, okay? So our machine learning is going to be trying to find, again, this one here is similar like a linear function here, okay? But this linear function here is not going to be deciding that, okay, I'm going to, give certain point on this side or this side. But it's going to be, I give you a particular value of the advertisement, then what do you expect to be the amount of sales? So if I can come up with a function, this particular linear function like this, or may not be linear, but some function like this, then I will be able to predict based on your input. I can give you the output. Okay, so this kind of problem, in terms of the model, you can say, it still is a linear, but actually the output is different. The output is going to be based on your input, trying to predict your output, rather than giving me two inputs, I'll predict, their classification. Okay, so this is another kind of, and so the many ways to try to find a model for or the solution for this kind of things. It's still similar. I mean, you can still see that we're still drawing a line. Okay, and when we draw this line here, it's still going to be a linear, okay, based on some input, okay, and we already have this one here. So many of the techniques that been designed for classification can be used for regression to try to produce output value according to your model, okay, and you still have the output, okay. So a lot of time when we are trying to do the machine training, okay, machine learning is to train the system so that it becomes to be better and better, okay? And we need to have some definition what is better, okay? Because we want our system to produce more correct output, okay? So we need to have some way to define, to say that how poorly our, some kind of hypothesis or how our prediction performs, okay? And so we need to define the loss function. And one way to define the loss function is to say that whether if your actual is correct or not, okay? So you can have a 0-1 loss function. So whenever I give you an incorrect result, okay, then your loss is 1. If I give you a correct result, then it's going to be 0, or something like that, okay? And you can see that this is probably not very good loss function, because sometimes your actual and your predicted may not be always exactly the same, especially for the regression. It's probably going to be within certain range. Okay, so if you use in this way, then it's going to be, you're going to get a lot of ones rather than zeros. Your 0 is going to need to be a perfect fit. Okay, so a lot of time we are not going to be, say, for example, here, that suppose that we define something like this one here, then we can define the loss to be something like, among them, okay, which one of them actually is correct or not, and then you can see that this is going to be a 0-1 loss. But most of the time, we are trying to, because we know that our system is not going to be perfect, our model will be perfect, we want to have some way to let us be able to measure a little bit more contiguous way to say that how good they are. And so we can use what's popularly called as L1 loss function, which is to say, from your actual output, from your actual result and your predicted, what is the difference? Okay, and we look at all inputs you have used for testing and to see that how good are they compared with the total output. Okay, and then we take the absolute value because we just want to know how far from the correct result. So you can think of this is to say, okay, here we have all of this here. Okay, and so when we try to compute it, we can be computing some of this. Okay, so if we have a model which is like this, then this is going to be the total distance we have, okay, from all of the inputs, okay. And so you can see that if we can find a line, find a line, okay, which is not going to be a perfect match for any nodes, okay, but still this line here is probably better than if you have a line like here. If you have a line like here, then everybody is going to still have some distance, but it's going to be farther away. So the total distance for every node to your model is going to be farther. Okay. So when we're doing the machine learning, L1 loss will tell us how good is your current model from all of the actual data by measuring the absolute distance. Okay, the sum of the total distance. Okay. Another popular way of defining the loss function is to use the L2 loss function, which is not taking the absolute value, but taking the actual minus the prediction, okay? And then take the difference of that and use the square, okay? Square value of that. So L2 and L1 both would give us the absolute value, okay? Both are going to be in the positive. There won't be any negative value. But this one here would do the square. So what does it mean? Square, if you have a big value, the square value will make it even bigger. Okay, so therefore this one here actually will make those big values to be even more severe. Okay, so you're going to try to make your loss function to be even more sensitive to try to keep the distance to be smaller. Okay, so this one here actually is something that we use more often. Okay, another concept when we talk about machine learning later is called overfitting. Overfitting is a way for us to say that whenever we use machine learning, sometimes, okay, we try too hard. Okay, we try to make our loss to be too small according to the input data. Okay, because we are being given some input data, but on the other hand, okay, what is important is not so much of how good is our model for all our input data, but it's going to be how good is our model will be whenever we look at some new data. Okay, and so overfitting is to describe the situation to say that a model which is too closely to a particular set of data, and therefore it may fail to generalize to future data. In the future, we're given some new data. If you have a model which is too close to your fitting for your current values, inputs, then it may not be good. Okay, so for example, like if you have data set like this, okay, one way we can do is to have something like this. And you can see, when you have something like this, then you're going to have this one here, which is going to be a loss. Okay, it's not going to be correct. Okay, because it's on the wrong side. However, this is the input has been given us. Okay, we can try to make it system or model better by creating something like this. And from the input data, we know that this is going to be perfect. Okay, but from the kind of a more general point of view, well, this one here is probably not reliable data anyway. Or this is probably something there's some special situation. Okay, it's not supposed to rain that day, but somehow there's some special, some kind of a big airplane just drop a lot of water out of the sky. Okay, so the condition doesn't rain at all, but however, you do see some rain. Okay, so those are really exceptions, and you shouldn't put that into the model. So comparing between this one and this one, I think we will agree that this one is probably better. Okay, and when you're trying to train your system, sometimes you shouldn't try to work so hard to create a very strange model like this, which would make your system to be perfect. But on the other hand, it is actually not general. Okay, so this is also another example. Okay, rather than creating for regression a line like this to predict, what your sales going to be, if you create something like this, okay, now if you try to use this one here to predict, if I have given you some, specific, advertising budget, you may come up with some value which is not, so close to, your desirable prediction. Okay, so when we are trying to do the machine learning, a lot of time, okay, to try to avoid the overfitting, sometimes that we create a cost function, which is to help us to decide whether we should continue to train or not, using not just the loss, which is the difference between the correct result and not so correct result, but we also put some complexity function here to try to say, oh, that's good enough. Okay, you shouldn't go too much longer. Okay, and we use some lambda as a hyperparameter to say, use some of the measurement to say that whether you should stop or not. Okay, or you should continue to train or not. Okay, or you should go into this way or not. So this is an artificial term, which sometimes is not measured by the actual loss. How good is your result compared with the actual result? But it's going to be based on some complexity of your algorithm. Okay, by looking at certain complexity of your, say for example, when we look at the linear function, it should be a very simple linear rather than a special curve. And if you have some special curve, that is probably too much targeted toward your specific input data. And so the complexity function here could be designed in many different ways. And in general, this will fit into what we will be discussing about what we call as a regularization to try to stop the training from continuing. Okay. So, okay, let's take a break and then we'll come back to look at some more, kind of big ideas about the learning, and also look at some specific examples, for our. Okay, so let's take a break. Given some input data, okay, and input data is a limited set, okay. So before we give it to someone to say, okay, this is our model, then we can try to split the information we already have into subsets, okay, and so that we'll be able to say, we have the information, we know the answer for all of them, but we're just going to try to train using part of it, and then the rest of that, we're going to test to see how good our model is, okay? And this is what we quite often called, holdout cross-validation, or more often used is, say, k-fold cross-validation. So k-fold cross-validation is to say, we have already some data, but since the data is probably, say, for example, some, small size. And so we decide to say, okay, out of this, we're not going to use all of them to be our training data, but we can just use some portion of it. Say we can use 80% to train, and then leave the rest of the 20% because we already know the answer of that. So we can use it to test our model, and we can see that how good our model really is performing, because our model can make the prediction, and then, because we already know what is the output supposed to be, so therefore we can check to see that how good those prediction will be, okay? And so this is a very often used, and this K-fold cross validation here, you can have a different percentage. Okay, you can decide to say, oh, here I have use 80-20%, or I can use 60-40%, or I can use whatever. Okay, just so that you have something that you can use for your testing to see how good your model is. Okay, because otherwise, if you have just been given, say, for example, some past information about weather, and now you have a new day that you're going to make prediction, then you really don't know how good your prediction will be. But if you use some past information, you say, okay, now I'm going to just use the past 9 months, and then I'll keep the rest of the 3 months of last year for our testing. Then I can test to see that how good our model is, because I already know what the result should be for that 3 months that I have not used for testing. Okay. So I have uploaded a program which is in our teams. Okay, and this is actually a program not by me, but done by from Harvard University. This is a program which is trying to train the model to test to see that whether you have a banknote, okay, or kind of your cash, whether it's a real one or is a fake one. Okay, and so let me see, the file they have given, okay, in addition to the Python, okay, there is this banknotes.csv. Okay, so if I open this, then you can see that it's actually is a table like this. Okay, so every line of the input, okay, actually has 1, 2, 3, 4 input features. Okay, let me see if I can make it bigger. Where is mine? Okay, so you can see that every line, every input line. Okay, now you cannot see this, but the first one is the variance, then the skewness, okay, the kurtosis, and then you have the entropy. Okay, so you have each line, you have these 4 different numbers, which defines. It's not giving you each of this as a picture, but this input data here already, kind of a process all of the pictures of each banknote, okay, to come up with these 4 numbers. And then finally here, the fifth one here is the cost, okay, and the cost, you can see that it has a 0 or 1. Okay, so let me just try to roll this up a little bit, okay, and so you can see that you have this, each line of this has some numbers here, okay, and so it has a total, I think it's maybe around 1,000 or something. I don't know exactly how many of them, okay, in this particular file. Okay, so what is this program is trying to do? Okay, let's just go through this. This is in Python only, so you can try to run this yourself, okay, and you can see that. So let me just show you what this is trying to do. Okay, so this program here, first it chooses the model. Okay, that is a model which has been specifically, some particular model from this sklearn. Okay, the scikit-learn. This is actually built just on Python, so you don't need to use a PyTorch. You don't need to use something. Okay, and they are already built. Okay, so you can just copy them. And you can either use SVM, or you can use perceptron, Gaussian, or you can use the K nearest neighbors that we have talked a little bit about. Okay, so you can first simply import the model from any one of this. Okay, if you use the K nearest model, then you can also define how many neighbors that you want to use. Okay, the default is 1, but you can choose to be 2, 3, or something. Okay. And then, so the model here, once you have selected, the first part of this program here, you can see that actually is to try to read the information from the file. Okay, so this is the file which I have just said is the banknotes.csv, which is included in here. Okay, so for every line, okay, you read from the CSV, okay, these banknotes, okay, then it would append this into the data list, and then each of the data list would have the first 4 numbers to be the evidence, which will be the input features, and then you will read the last one here to be the 0 or 1 to say whether it's authentic or counterfeit. Okay, so you can see that each line, each entry in this data here appended is actually a dictionary with the evidence mapped to label. And the evidence actually is a list of 4 numbers or features. This will be these 4 numbers. Okay, so you will be reading the information, okay, each one by one, and then take these 4 numbers into the evidence. And then this label here will be written as authentic. Okay, if this is 0, otherwise you will say this is 1 means it's a counterfeit. Okay, so the first part of this program here is simply try to create this particular input data structure, which is called data. Okay, so depending on how many lines you have, this data here would be a list of all of these different dictionaries. Okay, so here you can see that it is using this k-fold. So it is trying to say, out of the total number of lines we have in this file, okay, this is the length of the data, I'm going to take 0.4 of that. Okay, so they will give us, say, for example, if your input data here is 1,000, then this is going to be 400. So 400 will be my holdout. I'm going to keep 400. And then it's going to randomly shuffle the data. Okay, so the data given here is going to randomly shuffled. Okay, so all of this is going to be in a particular, not particular sequence. Then you will take from the beginning until the holdout to be your test data. So you now have a list, which is not the original list holdout, but you will be, not original list data, but you'll be from the beginning until that particular number. So it's 40 here, then it's going to be the test. So the first 400, if it's 1,000, the first 400 will be used as a testing data set. The rest of them, okay, will be from the holdout until the very end, it will be used for the training. Okay, so typically when we're doing the machine learning, if we're using the k-fold, this is the number k that you decide. What is the percentage of data that you want to use for testing, for training, and how much of the rest of them you can use for testing. But here you can see it's doing the random shuffle so that every time we run it, it's not going to be in particular sequence. Okay, because we don't know, we don't want the data is always trained only the first part. We want it to be trained using random parts, but it will be a percentage of the information that you have, for your data from your data set. Okay, so once you have decided what's going to be your training data set, then what it needs to do is simply to say, okay, now I'm going to put all of this, okay, I'll take the evidence. What is the evidence? Evidence would be the first 4 numbers. So this will be the features. Okay, the first 4 numbers, these are 4 numbers, and make them to be, all of this to be in training. So your training actually will be what? Will be a 2-dimensional array. It's going to be how many in the total of the training, which is 600, for example, and then each of that would have 4 numbers. Okay, that will be your training data set. And then why training here is going to be your label. You already know what is the label for each of this. Okay, so therefore this is going to be your Y. So you give the X and Y, both the training and the features and also the result, and you give it simply to the model that fit. So the model you decide here, whichever you want to use when you're using this the sklearn model, then this would train using all of that. If you look carefully, you can see that this Y here is a lowercase, but this X here is uppercase. What does it mean? the X is actually 4 numbers. It's a list. Okay, so usually when we are writing our Python program, whenever we have a list, okay, it's not a scalar, then we use capital letter. But why here is a single value is because it's only authentic or counterfeit. Okay, so this part here will do the training, okay, using part of the data. Okay, after that, then all it has to do is to simply say, okay, I already have the model trained. Then I'm going to now prepare my testing data. And I also have my testing supposed to be the golden, the ground truth. Okay, and that will be my label. And then we simply give this testing here to make the prediction. And we collect all the predictions. Okay, because now we're not going to give this one here to the model because the model is supposed to be making the prediction. So we simply give it only the input features. Okay, so now with that, we'll have the prediction. And how many predictions we will have? It will be the size of your testing data set. So this one here, again, the predictions will be a list of authentic or counterfeit. Okay, that will be the prediction. Okay, so and so now after we have done the prediction, so the next thing we do here is simply to say, okay, we're going to count how many correct we have, how many incorrect we have. So you can see here, we'll initialize them to 0, total to 0. Then for each of them in the testing, okay, and each of them in the prediction, then we simply say, okay, let's take them and check to see that whether they are correct or incorrect. If they are the same, it's correct. If they are not the same, incorrect. And the total is always increased by 1. So doing this for loop here, we'll be going through all of the predictions and check against the Y testing. And Y testing is from the original data. So therefore, we know this is supposed to be the ground truth, right? And so therefore, you can see that after we have done this, then we have the result. So we will have the, simply print out. Okay, you can run it yourself. You can see print out the result to say result from the model, this and that, how many correct, how many incorrect. So the accuracy can be computed by correct divided by total. And that will be our test. Okay, so this is actually a very simple program. Okay, you can run it, just one line, train the model, one line, do the prediction, and then just compare the result. And then you can see here, okay, the models is already built in this sklearn. Okay, sklearn is another package that you can download. Okay, it has many different. It has SVM, perceptron, it's a Gaussian, it's a k nearest neighbor. Today we have covered k nearest neighbor, and we have mentioned about the SVM. Okay, but they are just different mathematical model that you can use to train your system. Okay, in here is not really doing anything fancy. Okay, it's just simply say, well, I have the data, and just go ahead and train it to see how good it is. It is using some default, whatever you can go into the sklearn. Thing. Let me see here. Model here. Okay, this is the website that you can go to. This is the machine learning in Python, purely in Python. Okay, scikit. Okay, learn, and in this sklearn here, you already have the models for classification, for regression, for clustering, and for dimension reduction, and for different model selection, as well as it has all this pre-processing to help you to try to extract the features and things. Okay, it can also show you that the algorithm for cross-validation and other things. Okay, and this is everything is it's a community run. So if you just want to use Python, and if your system is kind of simple enough, okay, then you can still do it. You don't need to use Python, PyTorch, okay? But this one here, it is built on using NumPy. So you still need to have the NumPy. And the matplot library is just to plot, to show the output in the in graphs. So therefore, that this is something that you can choose to use or not. Okay, but of course that many of the example here, you probably have to use the plot here to see the output and this. Okay, so that's the example of the k-fold. Okay, k-fold means that how much you want to use the percentage of your information for you to do the training, and how much of the percentage that you want to use the rest of them you can use for testing. Okay, so another big topic is reinforcement learning. Okay, reinforcement learning is something very useful, especially if you want to build systems that can play game, can interact with human and can do this and that. Okay, so in the reinforcement learning, okay, the model is to enhance in addition to just say how correct you are. Okay, it is actually trying to say, I'm going to give you some reward if you eventually have done something. Okay, and so this is like playing games. Okay, or this is just like you're trying to train the machine to be able to kind of eventually say, for example, in robots, eventually be able to do something. Okay, and you say, okay, if you find a way to do it, okay, then you will get this reward. Okay, so in the reinforcement learning, okay, the model is a little bit different. Rather than just to say test to see that, oh, I have this input data here, I have the prediction, and I'm comparing the input from the prediction. It actually will have this, that I have this agent, okay, just like in our homework, right? Your whole agent is supposed to be taking certain actions, go move up and right or this and that, and you have certain environment which will stop you from doing this and that, okay? And eventually, if you reach, the environment here says that you've reached a particular city, then you get a reward, okay? And so the learning here is that these are the possible actions, but the machine will not make a decision. I mean, the human will not make the decision for the agent to say how you should do it, okay? But whenever you have reached certain stage or you have reached certain location, then you will receive the reward, okay? So therefore, the agent will try different actions, okay? And whenever it done some action, it get the reward, the next time you will know that, oh, I should do that more often, okay? So in the environment, when you are doing the actions, usually we have some kind of a Markov decision process to let us, kind of try to have one state to be connected to another state with certain either probability or certain likelihood, okay? So that we can take certain action when you are in a certain state, okay? So for example, like, when you have sunny day, then the likelihood for next day to be a sunny is probably going to be a little bit higher than if the next day is going to be raining, okay? And but on the other hand, that, there's always a possibility when you're coming from sunny into the rainy. So there is certain, kind of transition that you may make. So for example, you might have, if you have sunny day, and then in between you have cloudy day, and then the rainy day, then the likelihood for the sunny day to become to be cloudy day probably will be a little bit higher than become to be a rainy day, next. Okay, so your system probably will be defined with some state transition graph like this, and each of that, okay, as we said that, it could come up with some reward. Okay, so if you reach certain state, then this state here may come with certain reward. Okay, and there may be not just one goal state, but there may be many different individual rewards. And so, when the agent, when they are in a certain state, when you try to go, you may not know which one will give you the reward. Only after when you reach there, then you know that you actually get that reward. Okay, and so this is how the system is set up. Okay, so the Markov decision process here is that you have a set of state, and you have in each of the state you have certain actions you can take. Okay, and then you have some transition model from the state take certain action, then you go into which particular state. Okay, just like in our maze, that you go up, then or you will be in a different location, but you may not be able to move right or may not be able to move left and such and such. So there will be a transition model predefined, and then there will be some reward to say that if you're in a certain state, if you take certain action, okay, you reach some new state, and you also will receive certain reward. Okay, so here is similar to our maze. Okay, so if you go from there, you just want to kind of eventually go there, but you don't even know where that is. So you just simply say, okay, the system may come up with some of these red places that you are not supposed to be there. So if you go there, then you're going to get a negative reward. Okay, so at the beginning, you try to see if you go this way. If you go to the right, then you're going to have the negative reward. So therefore, you will put the red one here to say, don't go there. Okay, then you have to, your system would also try to go somewhere, and then you would find that you shouldn't go there. And so you just kind of, your system can keep going. Okay, let me see. This original. Okay, so you come here. Okay, this actually is a red. Okay, red one. So you say, okay, no, I shouldn't go there. Okay, and you put a red one there. You remember next time when you are in here, don't go to the right. And so therefore you can go to the up. Okay, and then you can come here. And next, okay, again, you don't know which one where you should supposed to go. If you go down, okay, again, you can get a negative reward. So you come back and say, okay, I put another one there to say, I don't go there. And you keep going, and no, you know that you're not supposed to go down, but you go up, then that is also bad. And you kind of been reset to say, down, you failed. And so you keep trying, okay? And then, here's another one. So you put another one here. And so you just kind of keep going, okay? And eventually you got it, okay? So reinforcement learning is a little bit different from the previous one. The previous one, we only checked the final result. But in this reinforcement learning, actually, your system will be getting reward that you'll try to learn along the way so that you'll be able to accumulate the best result. Okay, so the reward will be accumulated, and also when you are doing all of this, then you are trying to remember things that you have learned from the past actions. Okay, so it's the reward could be defined in the system, okay, but it could be also dynamic. So just like when we are trying to train our ChatGPT, okay, or something, actually it has gone through the training by interacting with real humans. Okay, after you have built a model, you actually would talk to the real human, and the real human would give the reward. Whenever you say something right, then you give the reward. And the system will remember that actually you should say that. Okay. So now, you would know that you should go this way and that way. This one here would be, kind of the way that you've tried before, you know it works, okay? But you definitely that you would know that you wouldn't go that way, okay? So you now will always follow, and you will find the right way, okay? Similar to our search program, okay, reinforcement learning, because it's trying different possibilities, okay? it doesn't always give you the shortest path, right? In our depth first search or breadth first search, you just know that whether you reach your final destination, whether you got your reward or not. And you remember you are not supposed to go somewhere, and so therefore that you will remember that, okay? But it doesn't always go to the right, kind of take the shortest cut, because you can see here, this definitely is not the shortest way. The shortest way should be either this way or it could be this way, okay? But that's how, when you have machine, will learn. Next time, okay, it may or may not know what to do or what not to do, okay? Another model is called Q-learning. And the Q-learning is trying to estimate, okay, when you are in a certain state, okay, then you receive a reward, okay, but you also try to estimate to see that if you go this way, are you more likely to receive some reward or not, okay? And this one here, so therefore you kind of need to have a function here to say that, okay, I'm going to have some estimate when I'm going to the, from the old state into the new state, how well I'm going to do, okay? And this is similar to like the machine learning, when you have the loss function, okay? You may not always trust this result, okay? Because after all, this is estimate. If we know for sure, some way it's going to be better, then of course you should go that way. But because this is an estimate, so therefore you might put an alpha there to say, well, I predict or I think this is the right way to go. And so therefore I'm going to go that way, but it may or may not give you the best result, okay? So the Q-learning is something that we probably will not talk about this too much in our class, because this is more about trying to do some of this learning that we'll be able to find the best way. And so for this class, that we are not going to go into those details. Okay, so we have talked about supervised learning. So supervised learning basically is that you already know what the result should be. So you try to train the model so that you will be able to produce a prediction, which is going to match your known result. Okay, and so you can check to see that, from all the algorithms we'll talk about that, we always have something to say we check against. Okay, by checking against something that make our training to be more kind of guided, because we know that we're going the right way. Another big area is unsupervised learning. Unsupervised learning, on the other hand, is there's no such thing as kind of correct result or not. It's more of, we have some information, okay, and see that whether we can use some algorithm, okay, we will be able to find something out from the input information, okay? We don't have any additional feedback, we just have the raw data, but we want to kind of learn from it. Okay, that's a machine, just say we have some garbage, okay, but let's try to see that whether the machine will be able to find out some information out of those things, okay, whether you can find any specific pattern, okay? And the very typical usage of the unsupervised learning actually is clustering. So the clustering is simply to say, suppose that you have some kind of information, okay? And here are just some distribution of information. And we are trying to see, out of this information, all this dots here, can we divide them into some meaningful group? Okay, different groups, okay? And so one algorithm, which is quite often used, is the k-means, okay? It's simply to say, well, suppose that, we have something like this, okay? And using k-means, we just assume that there will be 3 different clusters. So initially, we simply randomly said, okay, those are the centers of the 3 clusters. Okay, and we would use that. Then once we have set it, then we will try to find out, for each of the node, which is the kind of the center, class centers that they are closer to, they're closest to, okay? So from this, suppose that we have initially set this to be 3 centers. And for each of these nodes, say for example, like this one here, you try to check to see whether it's closer to this, or closer to this, okay? And it decides that the one that it is closest to, that the cluster is supposed to belong. So you can see in the first round, this is going to be, everybody is going to be finding its distance to there. And this one here is closer to here and farther from this and this. So therefore you say, oh, I should be in the green, okay? Of course, that after this, then you can see that, okay, everybody kind of say it belongs to certain cluster. And then after that, then we simply say, okay, now we assume that all of you are red. Okay, if we assume all of you are really red, then we'll find a new center for you. So we'll compute the new center for every cluster that is supposed to be, from the previous generation, clustered together. Okay, and so we'll compute the new center of the blue, new center of the red, and new center of the green. Once we have computed new centers, then we do this again to find everybody, to check to see that whether you should belong to which particular, you're closer to which particular center, okay? And then, so if you do it again, you can see that definitely for this one, you started it was green, but now actually it's closer to the center of the red, okay? So after this one here, if we done another computation, then you're going to find that, oh, all of them, this one here says I'm actually closer to you and not so close to you, okay? And so all of them will be, kind of the, and after this, you can see that this one here, okay, it says that it's closer to this, and this one here, it says it's closer to this, okay? And in this particular case, okay, you can see at this stage, we will again compute another round of the center. And this one here will then move the centers to all of this. Okay, and now we'll do this again and see that whether, each of them still think that they belong to that particular cluster or not. And if the next time they find, okay, that's true, then we have settled down. Okay, then we don't need to do it anymore. Okay, so this is unsupervised because we have just given you the data and let the computer figure it out. What's the cluster? It could be one information that we need to decide here is that how many centers that we want to initialize. Which here we will look at it at the beginning, we say we have 3, but it could be that, should be 4. Okay, and so that is something that you could decide just like at the nearest neighbor, you use 1 or 2 or 3 or 4, and this one here again, you can use the number of centers. You can decide whether you want to use how many do you, and sometimes that you should try it multiple times, okay, and see that with which one give you a closer. How do you measure? So here, suppose that you have 3, and if you use 4, what should be the difference? The final result from your 3 or 4. The total distance from every node to its center should be the smallest, right? If you have another center, which is kind of put something in here and some other belong to that center, maybe that center shouldn't have any node around it. So even though you have a 4 cluster center, but 1 cluster may be empty. Or maybe something like, for example, like some of them will be separated into 2, but total distance from the node to each of the center may not be as small or as big, okay, compared with, if you have less centers, okay? So that would be something nobody knows exactly how many you should have, okay? And you should try different ones. And sometimes that we can also define, similar to like in the machine learning, we use different hyperparameters or some initial numbers, initial parameter you decide. You can decide to use 3, you can just use 4, you can just use 5, and see which ones that give you the better result. Okay. Unsupervised learning, of course, that you can do it this way, and sometimes that will, even if you use unsupervised learning, you might have some quote unquote measurement to see how good your result is. Okay, and you need to define what it is supposed to mean for your specific problems. Okay, I think that's all I have, and so let me see if I still have my slide. So okay, so coming back to this one here. So what we have kind of done today is to introduce the machine learning nearest neighbor. We have talked a little bit about SVM without going into the details. Okay, we have introduced Python, PyTorch last time, and also some of the deep learning kind of a basic, flow. Next time, we're going to go into neural network, and we're going to the deep learning. Okay, and we'll be using from here. We'll be using some of the computer vision, and we're going to try to do something which is a little bit more real. Okay, we're going to see some real pictures. We're going to see some result. Okay, and so we will be, the homework 2 probably will be released at the beginning of October, so that you have a little bit more time to do it. And I expect that in the homework 2 you will start to use PyTorch to do it, because PyTorch has a lot of capability. And so again, how many of you have actually signed up? Log into the our system? How many of you? You've been given an account. Okay, try to log in to see that whether you have any problem. Okay, next time we'll probably try to spend a little bit of time to, kind of that everybody has a chance to do something. Okay, I may give you some small things for you to do. So bring your computer next time and see that whether you can log into the system, and so that you'll be prepared for the next project, which you probably will be assigned in October. Okay, any question? So remember, the homework 1 will be due not next Friday, but next Thursday midnight. Submit your project before the end of the day for the Thursday. Okay, then I'll see you next week.